Welcome to this NPTEL course on Advanced Pre-Stress Concrete Design. We will continue the previous module. We are talking about strut-and-tie model. In this lecture, we are going to talk about guidelines for formulating an efficient strut-and-tie model, and we will go through couple of examples. One related to the design of deep beam and another one is the design of a corbel using strut-and-tie model. What are the expected learning outcomes? The student, after going through this video, he or she should be able to gain knowledge on the guidelines for formulating an efficient strut-and-tie model and understand the process involved in design of post-tensioned deep beam using strut-and-tie model, and also how to design a corbel using strut-and-tie model. Now, let us go through the procedures or guidelines for formulating an efficient strut-and-tie model. The first one is, we need to provide, as we have discussed the various components of strut-and-tie model in the previous lecture, ties or tension element. When we form the strut-and-tie, we need to choose a configuration so that it is practical in providing that tie. For example, let us take this example number 1. I have a deep beam which is subjected to 2 point loads like this, right. So, I can come up with a very elegant strut-and-tie model like this. You can see the force flow is this. These are compression struts and directly force like this, right. And then we have here as well, it's a strut, and then we have a tie element which is like this, okay. So, this is a you can see that the tie is always either horizontal or it should be vertical. This is one configuration which we can easily visualize the force flow. It, the load goes from here to the support, right. And then you have ties are provided at the bottom to satisfy the equilibrium condition. It is a very elegant way of putting the strut and ties to transfer the applied external loads. Now, you can also have another configuration like this, right. This also is a safe design. So, you can have a compression tie like this, right, and then like this, then finally it has to go to the support like this, right. Now, to balance at this joint, now I have to put some ties which are tension element like this, right. These are ties. Right. Now, you see here in the model 2, the ties becoming an inclined member. So, generally to achieve that, the inclined configuration of tie within a concrete element is very difficult and cumbersome. Practically, it is difficult to implement. So, providing an inclined reinforcement in diagonal ties is difficult. However, if the ties are going to be oriented, you have to choose a configuration such a way that either they are going to be vertical or horizontal, and that would be practically feasible, right. So, though these both the models, if you look at it, this is more efficient from practical reinforcement laying out, right. So, this is also okay. I mean, this also will provide a safe design, but from practicality point of view, the model 2 option is not a good one. Okay, the next step, so next guideline, we have to make sure that the angle between the strut and tie should be kept greater than 25 degree. So, the angle between the tie and strut should be kept more than 25 degree. Now, you can see why do we do that. So, for example, same example, you see this angle, this alpha has to be greater than 25 degree, right. Why? Because we have seen that whenever you have a tension that is there, right, if it is very close to that of compression strut angle, the presence of tension will affect the strength of the strut. So, always we have to keep the angle between the strut and ties greater than 25 degree. Otherwise, the tension that is close to that strut will affect the strength of the strut. That let us explain why does that happens. For example, you see here, this is an example where you have a bottle shaped strut. When the strut is forming, also there is a transverse tension always will happen. Now, in addition to that, if you are having a tie element, the tension will become higher. So, this people have investigated. For example, you take in a shear element, always you have in the principal compression direction, you have a strut. In the perpendicular direction, you have a tension will be there. So, if I test a cylinder like this, concrete cylinder in compression, I get this blue color curve when there is no transverse tensile strain, or in other words epsilon r is 0. But the same cylinder, if I am testing it with some level of transverse tensile strain, you see that there is a softening effect that it is happening. So, this is called softening coefficient, which is xi. So, you can see here that the peak strength of the cylinder is coming down, and also there is a loss in stiffness, right. So, that phenomena is called as softening, right. So, this softening is going to reduce the strength and stiffness of the concrete. So, whenever you have a tension tie that is at an angle less than 25 degree, that will have a greater influence in producing this transverse tensile strain in the transverse direction to the strut, that will reduce the strength. So, that is the reason we need to make sure that the angle between the compressive strut and the tie has to be greater than 25 degree. Now, the third is we have to apply the beam theory at the interfaces between B and D regions. Now, in the last lecture we have discussed typically close to the where you have a heavy concentrated load or there is a geometric discontinuity, you have disturbed regions, and you need to go at least lateral dimension away from that region to get the Bernoulli region or a bending region, right. So, that is what we are seeing here. For example, if you see, you have a post tension beam with a heavy load like this, okay, compression load, and you form a strut like this, okay, strut and tie like this. So, if this is your depth h, then this is your D region, you have to move away by at least a distance h in the longitudinal direction. Then you start your Bernoulli region or a bending region. Now, what we are seeing here is at this interface, for example, I have two struts which are forming, which are AD and BC. So, it is going to produce compressive stress force FA and FB. That FA and FB should actually equate to the force that is produced, which is FAB in the B region. So, that is what we are saying. The summation of the strut forces at the nodes A and B, these are the nodes A and B, must be equal to the stress times the area in the B region, right. So, you add that FA plus FE should be equal to FAB, which is stress, which is we know that at the end of the D region we will have uniform stress distribution. So, stress multiplied by area will give me that force FAB. So, we are ensuring that, okay. So, this is one of the guideline. Now, the next one is very important thing, how do you orient your struts and ties? We can take guidance from the results of elastic analysis. For example, you do some simple finite element analysis, elastic analysis, you find the compressive stress and tension stress trajectories, then that will give us an idea where you need to put your compressive struts and ties. So, we have to arrange the struts parallel to the compressive stresses and ties parallel to the tension stresses. So, you can see for example that we have seen a corbel which is subjected to a load like this. You can see here tension stresses are this, okay. So, I have to orient my ties like this, right. In addition to that, some ties should come here, some ties should come here, right. Similarly, if you look at the compressive stress trajectory, you can clearly see here that you have basically compressive stress you have to form like this. Then in addition to that, you can see you have to form a strut like this and strut like this, right. So, that is what we are going to look at it here. You can see the red colors where we have expected from the stress trajectory, we have oriented the tension ties, the red color elements, and then compressive stress are exactly along the stress trajectories that we have seen from compression stress. So, in this way, doing an elastic analysis and finding out the stress distribution gives us a very good idea where we need to put our tension ties and compressive struts. Okay. Now, the next is you do not want to have a large strut. So, we can divide the large strut and we can utilize that available space. But in that process, we should not also overdo it. We can explain this through a couple of examples. For example, you see here there is an element that is subjected to heavy compression. So, larger struts like this can be divided to help in the placement of the reinforcement, and also it should not be divided excessively. So, that we can illustrate it. For example, this strut, what I can do is I can take this along this one strut and along this one strut and then go like this, and then finally take it back like this, right. It is a very efficient way of doing it. Of course, to satisfy the equilibrium, now I have to have some ties which are in the transverse direction. So, this is one elegant configuration. Now, you can also see that the ties are always either vertical or horizontal, right. So, it satisfies all the requirement. Now, I can also do the transfer the force by this. For example, I can have tension tie like this. I can have number of such struts and ties that are forming like this, right. So, but you can see here this is a very excessive doing of splitting the strut. We are dividing the struts into too many things, but this the first case, if you look at it, it is a very elegant way of dividing it. So, it helps us to put the reinforcement in a proper way. Now, you see here you have ties are all oriented at different angles and so on. They are not really either horizontal or vertical, and placing them becomes also very difficult. So, this is also safe design, but it is not going to be a very efficient design from construction point of view, and also the amount of reinforcement point of view also, it is not a very efficient design. So, we should not do these things. So, we should try to, for example, this case we have only one strut. So, that is also not good. So, we can do this, the next option which we let us say call that as 2. That is much more a practical way of dividing the strut. Okay. The next step is inefficient load paths shall be avoided. So, what is the meaning of inefficient load paths? So, let us look at it here. Now, here also if you see here, I have again simply supported D beam with 2 point loads, and we have seen is a very elegant way of transferring that strut is basically this. You strut orient like this, right. And always before the concentrated load, you have to try to orient a strut exactly below that, and then you put some node region, right, and then the tie is somewhere here. You put ties, right. Now, the second way also I can do is I can create a ties like this. Okay. This is also a safe configuration, but I can orient my compressive stresses like this. This is also a safe configuration. Finally, you see here I take this load and take it here, and then I take it here. So, this is what we are doing, right. And then to balance that, then again we need to have some tie element, right. So, that is why we are doing this. So, this is much more complicated way of doing it, and but both will give me safe design, but the second one, if you look at it, it is a inefficient design, but it is still safe from strength point of view, but in terms of putting the amount of reinforcement and then how do we construct it, it is actually not a very safe design. Next is we need to adopt systems that are both internally and externally statically determinate. So, what is the meaning of that? Right. So, let us look at this Corbel example. If I take a section here, right, whatever the force that we have, right. So, for example, you see here, then let us say this is the force that is P. So, if I take moment about any point here, for example, then P into this lever arm is your external moment. That should be equal to this internal moment. For example, the force, let us say F d times the distance, which is this, right. Let us say this distance is y, this is x. So, P into x should be equal to F into F t into y. So, or in other words, we have to formulate the triangulations properly, so that you end up with statically determinate trusses like this. So, the triangulation of struts and ties is very, very important. If you do that, you come up with a statically determinate trusses inside the element that you are doing the analysis, right. So, we have to make sure that the systems are both internally and externally statically determinate. Now, let us look at how do we use, we have now previously we looked at the 7 major guidelines on formulating an efficient strut-and-tie model. Now, let us go through an example on post tension beam, how we can use this. Before that, let us understand what a deep beam is. Okay. A beam shall be deemed to be a deep beam when the ratio of effective span to overall depth is less than 2 for a simply supported beam and 2.5 for a continuous beam. So, for a simply supported beam it should be less than 2 and for a continuous beam it should be less than 2.5, right. So, most typically the deep beams occur as transfer girders, which may be single span or continuous, right. So, sometimes the deep beam action also occurs in some shear walls and pile caps also. So, we will talk about that, right. So, this is your span and depth. This is very simple definition that is given by IS 456 just based on L by D ratios only. Okay. In addition to that, depending upon how the loads are acting, there is one more parameter which is called shear span to depth ratio. That also some of the international codes use for defining whether it is a deep beam or not. So, let us look at that. Now, why is it important? For example, this was one of the classical work that was done by Leonhard and Walther back in 1960s and 70s. They published this work. They took beams with the different L by D or L by H ratios. You can see one is with the ratio of 4, one is with the ratio of 2, one is with the ratio of 1 and one is less than 1. And what they found was, for the same load, they put some Dimick gauges and then they measured the strain variation along the length or along the depth of the beam. They found that when the L by H ratios were more than 4, they were getting very nice linear variation like this. But the moment the ratios become less than 2 and 1 and you can see that the stress distribution became highly nonlinear, then your Bernoulli's hypothesis is not really strictly valid, right. So, that is why we have to use deep beam concepts for analyzing whenever your L by D ratios become less than 2.5 typically. More than 2.5 typically we assume that still you can use section analysis to calculate the capacities, but anything less than 2.5 definitely it will behave like a deep beam and the stress distribution will not be linear or strain distribution. And this is another one definition. If you look at as per ACI, they have two things with which they define the deep beam. One is either the span to depth ratio should be less than 4 or shear span to depth ratio is less than 2 to 2.5, right. So, for example, what is shear span to depth ratio? This is where I am getting a load. So, I calculate this distance which is called shear span. That distance divided by depth I take the ratio. If it is less than 2.5, then you take this as a deep beam. So, you have to satisfy either one of the condition, either L by H is less than 4 or when your shear span to depth ratio becomes less than 2.5. Now, Eurocode defines span to depth ratio as 3 as a limit for considering that beam as a deep beam. But ACA, as we have discussed, when L by H is less than 4, it becomes deep beam, or when shear span to depth ratio, when it becomes less than 2.5, it becomes like a deep beam. Now, what are the different failure modes of the beams that you will have? So, we can look at it. For example, when your shear span to depth ratio, for example, this is what we say shear span, when it becomes more than 5, then you will have a flexure dominant failure, right. And typically, for conservatively, we take A by D ratio greater than 6, definitely you will have, based on all the test result that has happened on slender, reinforced concrete and pre-stressed concrete beams, when the shear span to depth ratio is more than 6, definitely you will have flexural failure. However, when the ratios are between 2.5 and 4, you will have shear dominant behavior. For example, you can have a diagonal tension failure like this, or you have this crack flexure shear crack forms, and then if the development length is not good, then you have a loss of bond and it creates a splitting crack. Or you can also have a localized shear compression failure after significant diagonal cracking. So, these are the 3 failure modes that are possible where for an RC beam that are tested between the ratios 2.5 to 4. Now, the moment the shear span to depth ratio becomes less than 2.5, then basically it is transferred, the load is getting transferred in the form of truss mechanism. So, where you can see, or an arch mechanism we can say. So, inherently you form a arch like this, okay, and then arch is nothing but basically or a combination of strut and tie, and but again to satisfy the equilibrium here the tie also should be formed, okay. Now, here I can also have a diagonal splitting failure, okay, and then finally in the deep beam it can also fail in compression close to the loading region as well, right. So, but we can clearly see that when the A by D ratio is less than 2.5, it becomes a deep beam and you form internally within the beam struts and ties. So, you have to locate the strut and ties properly, and you can use strut and tie formulations to calculate the capacity of the beams which are subjected to loads for which the A by D ratio is less than 2.5. Okay. Now, let us look at particularly about post tensioned deep beams. What are the advantages of going for post tensioning in deep beams? Typically for transfer girders, the load transfer is going to be very high, and to get economical design, post tensioning is used. I can also play with the cable profile to nullify the effect of your vertical load, right. So, and because we are applying pre-stress, of course, the performance at service loads is improved and it leads to smaller deflections. We have seen what are the advantages of post tensioning or pre-stressing in general, and you will not have any tensile stresses in the concrete at the bottom fiber under service load. So, crack free element you will get, and the anchorage plates whatever we provide like this, it is going to provide excellent anchorage for the tension tie at the outer face of the nodal zone, typically which are located above the supports, right. So, this is how. So, because we are putting anchorage plate, that will act as a very good anchorage system. So, the tie will not fail easily, right. So, that is one of the another advantages of going for post tensioning in deep beams.